Hi, everybody. I hope you're doing well. This lecture is to discuss the dynamics of a spin half system. And why to do that? Why to study such a simple system? Well, it's one of the main reasons it's because it is simple and it's easy to do the math, to make some calculations here. And also, besides describing spin half particles and their interactions with magnetic fields, for instance, it can be used to model two-level systems in general. So if you have a system which can be described by only two energy levels, it can be mapped to a spin half system. It's a pseudo spin half system. So two-level systems can be mapped, can be described or modeled by a pseudo spin 1/2. Okay, so that's the importance of studying the dynamics of a spin half. As an example, you need eventually to put more ingredients to that, but a two-level laser, when you have up an upper energy state, say E1, and a lower energy state, and the system here, these two levels can be modeled as a spin half system, right? So a two-level laser, right? It can be modeled by spin half, all right? So let's try to understand a little bit more about the dynamics of this system. I recommend reading chapter 2 of the book Modern Quantum Mechanics by Sakurai. All right. Well, you can find many other very good introductions to the dynamics of a two-level system. Okay. So in Sakurai, you can find it where the book says spin precession. Right. It is the problem which we are concerned about here, right? So spin precession is a very interesting topic. But I mentioned previously, and I am anticipating some facts right now. I mentioned that Pauli matrices, which are used to make calculations in spin half systems, are somewhat linked to rotations. All right, so they are connected in some form to rotations. All right. So what is a rotation? Rotation. A rotation is a linear transformation preserving the size or the modulus of a vector. All right? It is not a translation, all right? The tip and the head of the vector remains, the tip of the vector remains at the origin, say, and you rotate the object. So a rotation is a linear transformation, but with the main property of preserving the modulus of a vector, all right? So it's a very important issue here. It preserves modulus. Also, to fully understand rotations, you need to go a little bit more deeply into a mathematical theory called group theory. All right. So rotations are linear transformations which do form a group under some operations. All right. I'll not discuss group theory right now. So if you're interested, you can advance some topics here. But what I can say in advance here is that rotations in three-dimensional space are non-commutative or non-commuting operations. All right? Two rotations in general do not commute. Say a rotation 1 times a rotation 2 in general is different from doing the operations in the reverse order. All right? So take for instance this piece of chalk. Say this is uh, pointing out of of the board. Say it is the x direction, pointing to the right is the y-axis, and pointing upwards is z-axis. All right. So we have here something like this: z here, y here, and the x-axis is pointing out of the board. All right. So a rotation is characterized by an axis of rotation. All right. So say rotations by x-axis preserve all the components in that direction. So you rotate things in this plane, y, z. Rotations with respect to the z-axis keep fixed the components along the z-axis and change all the other components of the vector, and so on, okay, and so on. So consider for now, just to show the main idea, a rotation first by the x-axis and then by, say, the y-axis. All right. So first, remember, operators which are applied first appears to the right and then the left operators. All right. So consider we are rotating this piece of chalk relative to x-axis 90 degrees. All right. So we'll rotate in the direction from y to z. So the right hand rule applies here. So consider this is the initial position of the chalk. It's oriented along the z-axis, and we rotate it 90 degrees respective to x-axis. So we rotate x 90 degrees. All right, and then we rotate y, this rotation y here, by 90 degrees. All right, we will rotate 90 degrees with respect to the y-axis. All right, So we need to perform a rotation along the y-axis. It does nothing to this object. It just rotate, but it's a cylinder, so it stays right here. All right. So this is the final position here. I will put this is the first operation, but the final answer here, just for you to remember what happened. And if I perform the y rotation first and then the x rotation, so this is the first and this is the second operations. And remember, I can rotate in the y direction, so I rotate from z to x. Our initial position was this thing here, and I rotate first in the y-axis, so I need to rotate according to the right-hand rule, 90 degrees. So 90 degrees, it rotates the chalk to this position. And now I need to rotate 90 degrees with respect, so it points outward. So I need to rotate 90 degrees in x axis here. But this is just a cylinder, so it's invariant under rotations along its proper axis. So it does nothing here, and the end is just the chalk pointing outward. So you can see clearly that the first operation produces this position for this object here. It produces this. And the second operation, which is reordered, produces this result here. All right. So clearly, rotations do not commute in general. There is one exception, which is two rotations by the same axis. So you can rotate, for instance, with respect to the x-axis 90 degrees and then another 19 degrees, or you can rotate, say, rotate this thing here. Consider the z-axis for now, all right? Two rotations around the z-axis. Rotate 45 degrees first and then 30 degrees. You find the final answer here. But you can also rotate 30 degrees first and then 45 degrees, and you'll find your object at the same position. So rotations in general do not commute. But if they are performed along the same axis, they commute. So in rotations in a plane are commutative operations. But if you perform two rotations with two axes through distinct axes, rotations will not commute. All right, so this is very important thing here. So the group corresponding to rotations is said to be in three-dimensional space is said to be non-abelian because the operators, the generators, do not commute. So in say in R3, in three dimensions of real vectors, rotations are described by non-abelian. Abelian is a terminology which corresponds in the language for generators for a Lie algebra. It's the jargon to say they do not commute. So described by non-abelian generators. Right? I am anticipating some things. Some of the information you can find in chapter 3 of Sakurai. If you are interested in proceed, there will be more. Modern quantum mechanics. It's chapter 3, all right? But I'll stop here this discussion, all right? So, well, about generators and all that. But what I need to show you is this thing. Consider, and you can find it elsewhere, consider a coordinate system, x and y, say x and y, and you have a vector here, a vector A. It has components a of x, a of y, and now you want to rotate this vector by an angle of theta here, right? You rotate the vector, so it's the vector A prime. It has components a of x prime and a of y primed, all right? So the modulus of the vector A primed is equal to the modulus of the original vector. There are two distinct languages which are called the passive rotations, where you keep the vector non-changing. You keep the vector and you rotate the coordinate system in the direction of the vector here, so rotate in the clockwise sense, or you can use an active point of view, so active rotations. I'm doing here an active rotation, so you rotate the vector, right? There are two viewpoints. One, the observer is seeing from this viewpoint in the x and y coordinate system, the observer is seeing the vector rotating, it's active rotation, it's an active viewpoint. And the other viewpoint is the observer is fixed with the vector, so he sees the other reference frame, he sees a change in reference frame, say. It's a very crude interpretation, but there are two viewpoints. You can keep the vector fixed and rotate the coordinate system in clockwise sense here in this example, or you can do what we are doing, active rotation. You keep the coordinate system fixed and you rotate the vector in the opposite direction. So counterclockwise rotation here. This rotation is performed along a z-axis. So if this vector has some component along the z-axis, the component az prime is equal to az in this example here. But relating the primed components to the unprimed components of x and y, you find out something like this. A of x primed, a of y primed is equal to a of x cosine of theta plus minus, beg your pardon, minus a of y sine of theta. So this is a counterclockwise rotation by an angle theta. All right, the vector is rotating by an angle of theta. The modulus is preserved, the length is preserved, but components change. So ax is larger at first, and then when you rotate vector, the x component diminishes and the y component gets larger, but the modulus of the vector is preserved. All right, so this corresponds to a of x sine of theta plus a of y cosine of theta. All right, these are the rotations. It can be described by a matrix. So a matrix, which in this case is of the form an RZ rotation. So this rotation around z axis by an angle of theta corresponds, this matrix corresponds to cosine of theta minus sine of theta, sine theta, cosine. And of course, the z component is kept fixed. Vectors in 3 dimensions has 3 components, so nothing changes for the z component. Z component becomes the same. So the vector A primed, which you can write this way, it's equal to the matrix rotating around the z-axis. So I am saying that this z here corresponds to the axis of rotation. Another possible notation would be rotation, R for rotation, by the n axis and angle theta. So you can choose any axis here. So this n here would be the z direction, right? So I'm using this notation right now, and I can apply this matrix to the A vector, and the A vector, the original vector, is the same thing, AX, AY, and AZ, but unprimed. All right, so the vector, could write this matrix applied to this thing here. All right, and you find the result, the previous result we have found here. All right, and notice that rotations are described by something called orthogonal matrices. All right, so rotations orthogonal matrices in real spaces. All right, so the group for rotations in three-dimensional space, when you are considering only rotations, is called the special orthogonal matrices of dimension 3. Right? This is a group of all rotations. It's a group. All right? We'll talk about groups later, but if you want to just Google it, you can Google for the SO3. It's just rotations in 3 dimensions for real vectors, right? Vectors pertaining to reals in 3 dimensions. But there are representations of a group. Representations of a group are always possible by matrices. So the easiest way is to operate directly on the object. So you have the vector v prime is equal to a rotation matrix V, and this matrix here is a 3 by 3 matrix. And this matrix has a very interesting property for the case of proper rotations, just rotations. You do not reflect vectors, you do not translate, just proper rotations. Contained in this group here, the determinant of these matrices of an orthogonal matrix is just 1. All right. So 3 by 3 matrices satisfying this relation here and preserving the norm of the vectors, the modulus of the vectors, the modulus of the object, satisfy this and are called orthogonal matrices. But there are other representations which are not by using 3 by 3 matrices. All right? It seems a little bit weird to say that you can represent vector rotations using something in 3-dimensional space which are not 3 by 3 matrices, but it is possible. So you act on a non-trivial representations, and the simpler, besides scalars which do not rotate, are spin half objects, right? Spin half objects, which in this case are called Pauli spinors, which have two complex components, can emulate rotations, do the same thing, but with two complex numbers in place of three component real vectors, all right? So these objects, the Pauli spinors, are rotated by something which are linked, related to Pauli matrices. So the Pauli matrices provide 2 by 2 is the dimensionally of the matrices representations of rotation generators, right? They provide 2 by 2 representation of rotations, say very directly. Well, let me prove that by a simple example here. In chapter 2 of Sakurai, there is an exercise. You are asked to find out the relation of this thing here, in exponential of in dot some Pauli matrices. So this vector here is general unitary vector, theta over 2. So rotation over an axis n, and sigma dot a exponential of minus in dot sigma vector theta over 2. It is called to find the link between this vector here, the original vector, and the rotated one. It will be a rotated vector. All right. You can write things like this, right? And n here is a general thing. You can say it's a sine of theta, and it's not the same. It's not this theta. I'll use another Greek letters here. Sine of alpha, cosinus of phi, sine alpha, sine phi, and cosine alpha, right? So you have an n vector in three-dimensional space, x, y, and z. The n vector here, I don't know if you can see clearly, but what is this figure? But the n vector forms an angle alpha with respect to the z-axis, and projected onto the xy plane, it forms an angle of phi with respect to the x-axis. All right. So this is the n vector. The n vector is normalized to unity, but I will use a simpler form of this problem. All right. I'll use a simpler form of this problem, which is the following. Suppose you want to rotate over an angle of theta, by z-axis. So my unitary operator is of this form: exponential of I sigma z theta over 2. So my n vector corresponds to the z-axis. I am rotating things with respect to the z-axis. Z components kept fixed. So my alpha angle is equal to 0. In phi doesn't matter, but you can put 0 there also, and you'll find any phi angle. No problem with that. Just alpha equals to 0 will give you this direction here. So now you can rotate all the Pauli matrices, but since I'll perform this kind of transformation. It's a transformation for an operator, and this transforming unitary matrix depends only on the Pauli matrix along the z direction. It commutes with z, z commutes with z, so this does not change the z Pauli matrix. It keeps fixed because it's a z rotation, a rotation around z axis. All right, it does not change z components of vectors. All right, and but for the other Pauli matrices, I need to evaluate these things here. So if you want to evaluate this thing here, what do you get? Right? Let us see. Let me erase here just to find some more space. Sigma z here. All right, but I'll write right here. E to the I sigma of z theta over 2 sigma of x exponential of minus I sigma of z theta over 2. You can write, as we previously demonstrated, this is the identity matrix multiplying cosine of theta over 2 plus, this is first operator here, is the identity matrix multiplying the cosine, but usually we don't write the identity matrix, so I'll use conventional notation. So it's implied that you have a identity matrix here, plus I sigma of z, all right, and the sine theta over 2 here. The sigma x is in the middle, so multiply there, but I don't have space to continue to proceed there, so multiply here. Cosine of theta over 2 minus, because there is a minus here, I sigma z sine theta over 2. You can multiply all the things here. So find out this, multiplying this, you'll get cosine squared theta over 2 sigma of x, because this matrix I cannot forget, it's in the middle of the calculation. This, multiply that. And I have I multiplying minus I, it will give me a plus sign, but there is a sigma z, sigma of x, sigma z, and the sin squared theta over 2, right? But there are another terms. This term multiplying the first with the sigma x appearing after the sigma z, and this term multiplying this thing, multiplying that thing, all right? So I will find imaginary. These terms are always proportional to the cosine multiplying the sin function, or the cosine multiplying the sine function, theta over 2, right? But now I have, notice that I have this multiplying this minus the reversed order. So I'll have the commutator of sigma z with sigma x, all right? The commutator of that thing. Because I have sigma z multiplying sigma x, sin multiplying this cosine, this is the identity matrix here, it doesn't matter, because the identity matrix multiplying anything is that anything. And I have this thing here multiplying this thing here multiplying that. So cosine multiplying sine function, sigma x, sigma z, but there is a negative sign and the reverse order of the matrices. This is just the commutator. All right. So I have this result here. All right. Keep that in mind. I will just use the top, the board here. So I am trying to do U dagger, sigma x, U. This is the operation I'm trying to do. I will have, notice, cosine squared, and this term here, I can commute the two matrices, but I get a minus sign because Pauli matrices anti-commute with each other. and sigma z squared is just the identity. So this term here, this thing here, produces minus sigma of x. And this commutator here produces twice the imaginary unit sigma of y. All right, this is the commutator. This commutator here produces twice the imaginary unit sigma of y, and therefore we have sigma x can be put in front of that, cosine squared theta over 2 minus, because there is a minus here, sin squared theta over 2, right? And here, twice the imaginary. The imaginary here, I get a minus sign. So minus twice the imaginary sine theta over 2, cosine theta over 2, sigma y. All right? So that's it. That's it. But now you can use two interesting trigonometric relations. This thing squared here, this identity corresponds to the cosine function of theta, and twice the product of, well, this imaginary disappears from here, right? Because you can see in the previous board here, there was a I imaginary times the imaginary, you get a minus 1, all right? So that's because this minus here. And the imaginary, of course, disappears from the equation. And this twice, this thing, twice the product of sine theta over 2 cosine theta over 2 is just the sine function, right? So we arrived at the desired result, which means the operator, U dagger, sigma of x, the operator, right? This operator applying to sigma x, and the transposed operator here, it doesn't matter what you call the transpose, the complex transpose operator here, but you find this as cosine of theta sigma of x minus sine of theta sigma of y. Notice the resemblance with the rotation by an angle theta of vectors. Here you can think that you had a sigma of x direction here, sigma y, and then you rotate these matrices here. Now you have a sigma x primed and a sigma y primed, say. All right, they are rotated. The Pauli matrices are rotated. You can also show that the following result. So for this thing here, this operator, for this operator, minus I, the z component of the Pauli matrices theta over 2, this operating to sigma x corresponds to rotated versions by an angle theta of the Pauli matrices, sigma x, sigma y. So we'll find out this thing here. Right, it's a general result. And in this case, of course, the z component keeps untouched, or it doesn't change because your operation is around z axis. So you're rotating the sigma x and sigma y matrices, but not rotating the z component. All right. But now, if you use this thing, you could do the rotation by an angle minus theta. So you get a plus here and a minus here. It doesn't matter. You can change the sign of theta. Theta is just the only restriction is must be in real numbers, right? So now notice that a vector sigma dot a, which is the original vector, corresponds to ax sigma x plus ay sigma y plus az sigma z. Now you can perform this operation. You can perform. I'm considering just this case here, a particular one. All right. Sigma dot a u, and this will transform this matrix, keep this matrix invariant under this operation here, and you'll find that you can put sigma x in evidence ax cosine of theta minus plus, I guess, ay sine of theta plus sigma y. You can demonstrate all these things. Ax sine of theta. I get a minus here for the sigma y, so this get minus here plus ay cosine of theta plus sigma z az, and this is sigma dot a primed. So you get the vector rotated. All right. So Pauli matrices are 2 by 2 matrices which allow me to do rotations. So I rotate vectors. So notice that we rotated the Pauli matrices in one direction, but I can also consider rotating the vector components, rotating the opposite direction. So Pauli matrices rotate by an angle of theta and vectors by an angle minus theta, and I can fix the directions here, the directions which are the Pauli matrices. All right. So, but notice this is just a rotation for the vector. The vector, the original vector now is a primed. This thing here is ax primed. This thing here is ay primed, and this thing here is az primed. But az doesn't change because I am rotating around z axis. All right. So Pauli matrices do perform or perform rotations in vectors, but instead of using 3 by 3 matrices, I am using a 2 by 2 representation of the rotation group. All right, the group SO3 is being represented by something we call SU2. Right? There is a correspondence. In fact, there is a 2 by 1 correspondence. There are two objects here. They are unitary matrices. There are two matrices here corresponding to just one rotation here. All right, but apart from that, this group here, which is the SU2, the special unitary of dimension 2, this form of matrices here, these are the SU2 matrices, can do the job for representing with more things in there also, but they do the job for representing rotations in 3 dimensions. All right. So there are objects which transform according just to this object here, but there are objects which are two-component complex vectors in Hilbert space which transform according to this thing here, which is the special unitary matrices of dimension 2. And the generators, the matrices which are linked to the rotations, in this case, rotation around z-axis is the sigma z matrix, are called the generators of the group. Generators. So sigma y, sigma x and sigma z are called generators for rotations, right? Generators for SU2 transformations are these matrices: sigma x, sigma y, sigma z, right? And these matrices, we already know they have a very specific algebra and cyclic rotation, cyclic permutations of x, y, and z here. They have the property of being anti-commuting matrices in this case. This is a Kronecker delta. But that's it for rotations, all right? So I want you to understand that Pauli matrices can represent rotations. They are generators for rotations, all right? Well, so much for that. I hope you can understand things. You can do all the calculations, all right? So let's try to understand what Pauli matrices do exactly. They are linked to rotation. So Pauli matrices, we did that by example, via examples, but you can demonstrate. It's beyond the scope of this lecture, but I can demonstrate in full that Pauli matrices are linked to rotations. Also, I already mentioned previously, there is a link of Pauli matrices with quaternions. If you are interested in the subject, you can just Google it, quaternions, and you'll find out some links between Pauli matrices, rotations, and quaternions, all right? But now, let us remember a few things of electromagnetism. So now we just change the subject a little bit to a thing in electromagnetism. If you want to discuss the Stern-Gerlach experiments, which we mentioned previously, but we did not discuss the details, you need to understand something called the magnetic dipole moment. Or, for the sake of simplicity, the magnetic dipole of a particle, right? So what is it in reality? So I will not make a huge, I will not submerge into the electromagnetism because it's just another subject. But remember that the magnetic moment, I will call it mu, the Greek letter mu, it is just in modulus a current multiplied by an area here, all right? So it's just current multiplied by area. So and the vector is just in the direction perpendicular to the area, all right? So if you have a current circulating and the area of the loop is A, the current is I here, you'll have a direction of the magnetic dipole which points by rule using the rule of the right hand points perpendicular to the area of the loop, all right? So consider, for instance, just a single electron in orbital motion. I am considering for now orbital motion, all right? And current in that case for orbital motion, it can be an electron or a proton or something else, but with charge Q is a point particle. Suppose it's a point particle. And if you're measuring the charge which passes through an area here, you'll have a charge Q divided by some delta T, and this delta T corresponds to the delta T is equal to the length of the loop, which is 2 pi r. The r is the radius of the loop, divided by the velocity of the particle, all right? So I will have here a current which corresponds to twice twice pi r, and well, let me see, I must invert that. I must invert. So I'll have q multiplying the velocity. I must take delta t to the minus 1. So this is qv divided by twice pi r here. So this is the current of this loop. Suppose it's just a single charge orbiting something here. It can be a charge of opposite sign, for instance. All right, so it's orbiting. All right, so it's orbital angular momentum. And the area of a circle, we already know what it is pi r squared. So we can compute the modulus of this thing here. All right, we can compute modulus. In this case, the modulus of the magnetic moment, just the product of this thing by this thing. The pi factor is removed, and you'll find out this is q r v divided by 2, right? The charge of the particle, the radius of the orbit, multiplying the velocity of the particle. But if you remember classical mechanics, you can remember that this area can be obtained by performing a vector product of r with or a cross product of r and the velocity. So this area is just proportional, the direction of the area is proportional to the r dot v, and I can write then that the vector mu is the charge over 2 r vector v, vector cross product with velocity. And the velocity of a particle is just momentum, linear momentum divided by the mass of the particle, all right? In this case, you'll have that the magnetic moment of the particle is given by, or the magnetic dipole of the particle is given by q over 2m r vector p. This is the classical object here. But remember that r v cross p is just the orbital angular momentum. So this is the definition of angular momentum. And this way, you have that the magnetic moment of a particle is just a constant for that particle, which corresponds to charge divided by twice the mass, multiplying L, which is the angular momentum, the orbital angular momentum, right? So in some sense, the magnetic dipole is proportional to angular momentum, all right? But we always can quantize in quantum mechanics. We need to quantize things, and I will not give you right now a lecture on orbital angular momentum quantization, but remember that we can rewrite this thing here as divided by h bar. So we will have the angular momentum measured in units of h bar, so integer units of h bar, and you can rewrite this thing with charge h bar here, so you multiply by h bar and divide by the same thing, divided by twice the mass, and this number here, which corresponds to charge multiplying h bar divided by twice the mass, is called the Bohr Magneton of that particle. All right, so h bar q divided by twice the mass is Bohr Magneton. Well, we can define the Bohr Magneton for electrons, and in this way, if you plug in the sign of the charge, it would give you a negative number, but you can also define this as a modulus of the thing, and sign will need to be explicitly written here. So you write charge as plus or minus the modulus of the electric charge, the electronic charge, and, or it can be another multiple of that quantity, for instance. But this is called the Bohr Magneton. All right? You can calculate the number here if you are interested in calculating the number here, right? But what happens for spinning particles? Okay, historically, it was Uhlenbeck and Goldsmith which thought about electrons or fundamental particles as having some kind of intrinsic orbital or sorry, intrinsic angular momentum which corresponds to rotation around an internal axis, and spin was the name of that thing. We know that point particles are not spheres, so the classical picture is not perfectly correct. But you can think about electrons, instead of orbiting something else, are just small spheres rotating around a given axis. And this is called the spinning electron, as if it was a classical sphere. All right, it's just a point particle, and spin is a quantum object. But originally, it was thought that it was just like a small sphere rotating around an axis, just like the Earth rotates through its rotation axis. All right, and that, because electrons are charged, that also produce a magnetic dipole moment. If you have charges moving in circular motion, you have a dipole moment. So a dipole moment for spinning particles corresponds just to the charge divided by twice the mass. I can also put the h bar here, and the spin of the particle divided by h bar. But the spin of an electron is just 1/2 h bar the Pauli matrices. All right, for a quantum electron, this is the case. So you'll have the magnetic moment of a spinning particle. So spinning for something like internally rotating spinning. That's the origin of spin. Is just the Bohr Magneton. All right, the Bohr Magneton, and the Pauli matrices here. But there is a G factor for the particles which links the spin to the dipole moment. So you can plug in a G factor here, which is called the gyromagnetic factor of the particle. It's an intrinsic property of that particle, right? So a magnetic moment is somewhat linked to Pauli matrices. A magnetic moment, or dipole moment to be precise, is linked to Pauli matrices for, of course, spin 1/2. It is called spin 1/2 because when you measure that thing, you find that in units of h bar, divided by h bar, you measure plus 1/2 and minus 1/2. That's the origin of the name, spin 1/2. The internal degrees of freedom corresponding to something like rotations, internal rotations, right? But it's just a point, so a point particle, it's not a sphere properly. It can have internal, it can has internal degrees of freedom, spin, and this spin, when you measure, you find two possible values in terms of relative to h bar units or related to h bar units. If you divide by h bar, you have two eigenvalues, plus 1/2 and minus 1/2. That's the origin of the name, right? Okay, but if you remember classical electromagnetism, you find that a potential energy can be attributed to a magnetic dipole immersed in a magnetic field of a magnetic dipole immersed in a magnetic field. It is given by something like this. I will call U, or subindex M to remember magnetic, is equal to minus the dipole moment scalar or dot product with the magnetic field. This is from classical mechanics, all right? And this kind of energy, if you calculate, it produces a torque, right? Tau, call it tau, which is proportional to some constant. I'll write, suppose you are measuring in proper units these things. It's proportional to this cross product of me cross the vector field B, all right? So if you put a magnetic dipole which is oriented this way and a magnetic field oriented this way, if you allow damping factors, which corresponds to attenuation, to losses, this thing will rotate till it finds the direction of B. All right, you can do that experiment using a magnetic needle in the magnetic field of Earth. If you just take out of the equilibrium position the needle, it will return to the equilibrium position. But if you are considering a lossless system, all right, lossless system, it is classical. It does not be to be quantum mechanical. In classical mechanics, you also have a precession. So consider a lossless system. There are no attenuation. In the case of the needle, you have attenuation because of friction forces, and it will relax to the most favorable situation, which corresponds to the lowest energy possible here, which corresponds to a parallel orientation between mu and B, or anti-parallel if mu is negative, but supposing that this corresponds to a positive vector or positive in some direction, this thing here will find a will get oriented in the same direction. They'll be parallel and you'll find the lowest possible energy. All right, if you have attenuation, if you have losses, the friction will produce, suppose this is the magnetic field of the Earth and this is the needle. If you put this position, it will just oscillate a little bit, and when energy stored in the system is lost, is lost to friction, to heat, it will just align to the Earth magnetic field. All right. But when you have a lossless system, you can do that in some situations, at least approximately for some time scale, and you have a magnetic field pointing upwards, say, and a dipole, your needle, perpendicular to the field, it will rotate. If lossless, if the system is lossless, it will rotate forever. This is precession. All right. So if it's not exactly at 90 degrees, but at some angle here, it will precess. It will precess. All right. And then this is the nature of the problem we are dealing here. Right. This is the nature of the spin precession problem. It also happens in classical mechanics. All right. But in quantum mechanics, this energy is represented by a Hamiltonian. So the Hamiltonian for spin half particle is something like this. It's operator because the Pauli matrices are matrices, as the name says. And you will find here a G factor, a minus or a plus. It depends on the sign of the charge. If an electron, you get a plus sign. If a proton, you get a minus sign. This magnetic number here, this Bohr Magneton, depends on the mass. So usually for nuclear particles, this is called the nuclear magneton, nuclear Bohr magneton, or just nuclear magneton. And you have this thing here, plus or minus is this thing here is the magnetic dipole in quantum mechanics, dot B. This is the Hamiltonian. So a plus for negative charge, and minus for positive charge. All right. Forces, which are the origin of the ideas behind the Stern-Gerlach experiments, that forces emerge as a result of gradients of potential energies, the negative of potential energies. You can see that from classical mechanics. So in this case, you have magnetic moment, and in classical mechanics, you would expect the gradient of me dot b here, because if you suppose a minus sign here, you'll find the gradient of that thing. But this thing here, it doesn't change with position, because it's just apart from direction, it's just a modulus is considered to be a constant of that particle. It's a feature, it's a characteristic of a particle. And then in order to produce forces, you need to insert the gradients of magnetic fields. So in Stern-Gerlach experiments, in Stern-Gerlach type of experiments, you need to have gradients of magnetic fields. And in quantum mechanics, uh, this force is just another operator, a quantum operator, because this Pauli matrices here. All right, so in quantum mechanics, force is an operator acting on some Hilbert space, and the average is what you really measure in practice in the real world. But Hamiltonian is just this thing. Well, to just to finish this topic here, I will make another video, but I guess this became too large for now. I'll finish right here. But I must remember that there are particles which doesn't don't have charge, like neutrons. They don't have charge, but they are composite particles. So externally, when you see a neutron, it has no electric charge, but it has a magnetic dipole moment. So uh, and the sign must be measured experimentally. And if I remember correctly, it's a minus sign. It's a well, I guess you need to plug in a plus sign here because this G is negative, right? And minus minus will get plus. So for neutrons, they don't have charge, but they have this thing here. They are spin half particles. So protons, electrons, and neutrons, they have they are all spin half particles, and they have a dipole moment, all right? And they couple to magnetic fields. And the description of the result is provided by this Hamiltonian when you look only at the spin degrees of freedom, all right? If you're interested only in spin degrees of freedom, this is the Hamiltonian. So the system can have orbital levels, you can have principal quantum numbers in atoms, but if you are interested only in spin degrees of freedoms, you just don't need to worry about kinetic energy and all that because suppose it's already known, and you have a quantum system of just two levels described by a, a Hamiltonian of this form. All right, so I'll come back now to calculate the quantum dynamics of this quantum system. All right, as an exercise, just to finish, find these equations of motion for classical magnetic dipole. Suppose it's a classical thing, mu, all right, which have which has components. Find the equations of motion explicitly. Just write down the equations of motions. It is given by this kind of equations, just a gamma factor, which is a numerical constant here. It corresponds to a torque exerted on angular momentum. You can just you can justify this equation and find the components of this equation. All right, it's classical. And if you want to just describe relaxation, you can put another term here which corresponds relaxation. You just insert another term of the form mu divided by some tau factor, or there are another forms, the Ginsburg-Landau semi-classical equations, and, and sorry, it's a Landau-Lifshitz-Ginsburg equation, all right, which has a phenomenological term corresponding to damping, to loss in this system. But a classical system without loss will be described by this thing here. Suppose, for instance, B is in the z direction, all right? Just to simplify things. So simplify the problem to this and solve this problem, all right? So bye-bye. See you next time.